I'm going to talk about Ethereum in terms of the spec, which is where the Ethereum system is defined. This is like the blueprint kind of. The eth-research forum, that's where the spec is updated and refined and where new changes are proposed and debated on. And how the spec is implemented by the clients, how the client code is run by these various computers around the world. These are the nodes. And how all of that results in the Ethereum world computer system that we use and know. So yeah, the main thing here is the spec. The spec is, like I said, it's kind of like the blueprint for the system. The spec is kind of the source of truth for how Ethereum should work. So all of the kind of important features and aspects of the system are defined there. So for example, you have stuff like what a block looks like. You know, blocks have certain fields. They have like the difficulty. They have a block number or height. That's just the sequential block number. They have obviously the transactions, the transaction root. So they have all these fields, and you need to define that clearly. And where it's defined is in the spec. Another example would be with accounts. So all Ethereum accounts have a balance and a nonce and a storage hash root and a code root hash, whatever. And for a regular account, like an Ethereum account that you might have with some ETH in it, you don't use the code hash or the storage hash. You just have a balance and a nonce. But all of the like a contract, for example, it's still just an Ethereum account. It's actually the same kind of thing, more or less. But it uses those two, the code hash and the storage hash. So anyway, the spec, you would define like what do accounts look like, and in the spec it defines exactly that. Like you have these 4 fields, and with a externally controlled account, which is like a regular account, like a MetaMask account, you only use the first 2. But anyway, all that's defined in the spec. And you would also define something like the difficulty, right? So with Ethereum being proof of work right now, it has it's still using proof of work mining, and you have like the difficulty algorithm. So in order to know when a block is valid, like a new block being mined, you check the difficulty algorithm. So you would there's the nonce inside of the block, and the nonce is being permuted such that you hopefully get this block hash that has enough leading zeros, like it's a low enough number, such that it's like accepted, right? And anyway, the way that you do that is defined in the spec. Like, what is sufficient difficulty threshold for this block? There's an algorithm for it. It depends on the average block time of the last, like whatever, 1,000 blocks or something. I don't know exactly. In Bitcoin, it's the last 2016 blocks, I think. And it's like, if on average those are taking too long, then make the difficulty a bit easier. And if on average they're going too fast, make the difficulty a bit harder, right? So you need to define that super clearly. Like the spec has to define exactly how you calculate that difficulty thing, because all of these nodes have to, arrive at the same conclusion. If one implementation is a bit different and it thinks, okay, this block's valid, it passes the difficulty threshold, and then another set of nodes disagrees, then you have a fork, and they have a different history, and the whole thing doesn't work. So another area where this is really important is with the EVM. So the EVM is the Ethereum virtual machine. This is the thing like at the center of Ethereum, so to speak, that computes the state change for every transaction, right? So Ethereum is like a state machine, like it's this big system. You have all of these accounts. Each account has like a balance, the nonce, everything I mentioned. And then the contract accounts, they have like the contract code and then some storage for the contracts, right? So that's like the entire Ethereum system. And whenever a transaction happens, the Ethereum virtual machine is the thing that takes the previous state, looks at the transaction that's just come in, computes what changed in the Ethereum system as a result of that, right? So it computes the new state as a result of that transaction. And yeah, so the way that the EVM, the Ethereum virtual machine, does that, it has to be the same, like it has to be super precise, right? Because if you have these different clients and they do something a bit different with the EVM, then two different clients could process one transaction, and maybe they get different resulting states, and then the system forks, and you don't have consensus, and the whole thing kind of breaks. So yeah, for example, like in the EVM, so the EVM is kind of like, it's kind of like if you've ever looked at assembly code, like if in a regular CPU and a regular computer, you have your processor, and everything your computer does is ultimately compiled down to assembly code. And the assembly code is something that the processor can actually interpret. And the assembly instructions are super, super simple. They're like, you have some registers, and it'll be like, registers are places where you can store some data. And the assembly instructions will be like, store this value in register 1, store this value in register 2. Then you might have like an add operation. So at the assembly level, the operations are very simple. Like I don't think you would have like exponentiation, but you'd have add, multiply, subtract, stuff like that, right? And so the assembly instruction might say, add the contents of register 1 and register 2 and put the result in register 3, right? So anyway, that's like regular computer world. In Ethereum, you have a virtual machine. So it's kind of implementing something similar to that kind of system, but it's not actually running on like the actual processor at that level in the same way. Like it's a virtual machine, so it's actually, we're kind of like building the same sort of low level, super simple machine, but it's all built in software. So it's many layers, like when it's actually running on your computer, it's in a sense many layers above like the CPU level. Ultimately, it all gets compiled down to the CPU anyway, but anyway. So yeah, so anyway, the EVM it has these super simple opcodes, and the opcodes are things like similar to the assembly. So you have stuff like add, multiply, subtract, hash, compute the hash. That's one that you wouldn't see in a regular CPU. But yeah, the EVM will have all these opcodes, and all of the contract code, like any Ethereum contract you interact with, what actually gets uploaded to the Ethereum system is the bytecode. So people write their contracts in like Solidity or Viper, and then they're compiled to EVM bytecode. And the bytecode is like the assembly, in regular CPU world. The EVM bytecode is like assembly, where it tells the EVM what to do in these super simple operations, like, pop. It's a stack-based machine, so rather than registers. So it'll be like pop the two values off the stack, add them, and push the result back onto the stack. So anyway, the EVM has these basic operations like add, multiply, subtract, and so on. And the way you actually implement these is if you read like the Geth source code, you can find where the EVM is actually implemented. And this is really interesting because all it is like there's an add opcode, right? And there's just a function, a Go function called add, and it simply takes two operands and adds them together and returns a result. And yeah, that's kind of interesting because you might think, why would you write an entire function to do something as simple as add two numbers when Go and any language has a built-in like add operation? So why would I write the whole function? And the reason is, like in Ethereum, for example, the Ethereum virtual machine is defined such that it uses 256-bit numbers for everything. And so when you do add, you have to make sure that when you're writing your function that performs add for the EVM, you have to make sure that it does that within the constraints of 256 bits. So for example, if you had the largest 256-bit number you could have, right, which would be 256 ones for each bit, and the size of that number would be 2 to the power of 256 minus 1, right? So if you took that number and then we're adding that to 1, like you have your two numbers, they're both 256 bits. One of them is the maximum number you can have in that width, and the other one is just 1. But because the first one's the maximum you can have, when I add this other one, it's if you're constraining the number to stay the result to be 256 bits, it's going to roll over because it doesn't have any more room. It can't expand and add a digit, which it would need, a bit. So anyway, what you expect and what should happen in the EVM is it should roll over. So 2 to the power of 256 minus 1 plus 1 should give you 0, because the whole thing should just, it can't expand it, so it has to just go back to 0. And yeah, if you naively just thought, well, we'll just use the add operator in like Python, because it's just adding, right? And we'll add these two numbers. Well, Python doesn't care how big the number is. It can go easily have like 1,000-bit numbers. So you'd get a different answer, right? And now your system forks because there's a difference in how the EVM functions on these two different implementations. So anyway, the spec defines all of that very carefully, and then these various clients implement the spec. And I'll also say a little bit about eth-research. So the spec is kind of the source of truth for Ethereum and how it functions. eth-research is where these like new changes and proposals are developed and where they're discussed and where they're refined, and eventually they make their way into the spec and change the spec, right? So you take something like EIP 1559, which is the fee burn mechanism that made its way through eth-research and there's a thread with like, I don't know, thousands and thousands of comments. And people discuss it and they refine it and so on, and eventually it makes it into the spec. And actually this isn't quite as like linear as a flow as it looks. These, like the client teams that actually write the code to implement the system, they provide their feedback and they participate in eth-research. So this is all really like one, circular thing kind of. And yeah, so anyway, ultimately the spec is implemented because the spec is written in like, it's quite formal, it's written very clearly, but it's generally not code. Sometimes you'll have a reference implementation written in Python because it's easy to read. And I think there is a Ethereum reference implementation, but that's not meant to be actually run on computers, on actual nodes, right? So it's there to just provide this reference. But ultimately, people have to actually write the code to build this machine, the system that's defined in the spec. And what we have in Ethereum is we have there's at least 5 different client implementations. There might be more now. These are the teams that take the spec and they build it into a thing you can run on your computer, right? And they're written in different languages. So here's a few like Bezu, Open Ethereum, Geth, Nethermind, Aragon. Geth is the most popular. It's written in Go, but we have Rust, Java, C#, another Go. And yeah, so there's all these different clients, and there's lots of reasons for having multiple clients. So for Bitcoin, for example, there's just one client, and like you can make some arguments for that being a good thing. Like it kind of reduces the surface area of things you have to worry about, right? There's one implementation, just make sure it's super solid. But the counter to that is when you have multiple clients and then the nodes in the system are running a diverse set of clients, if there's some random bug in one of these clients, it doesn't take the whole system down, right? So especially if it's a minority client or especially even if the nodes, say like we have 5 nodes, 20% of nodes are running this, 20% are running that, 20% are that, then any client can have any kind of catastrophic failure, and the system should run just fine. There shouldn't be any real issue. Because like assuming that the error happens in one client, say 20% of the nodes fork off and they have some error, they're on a wrong fork, the rest of the network, the majority, will stay on the proper fork and everything should be okay. It does get a little complicated if you have like geth, which I think has close to 50% of the network. Close to 50% of the nodes I think are running geth. So if there's a problem in geth, it is more of a big deal. But anyway, like having multiple clients like that is good because it increases the resiliency of the system. Right, and yeah, so there's other reasons you can have multiple clients. These different clients can make different optimizations and trade-offs. So you can have, you could have a client that's optimized for, you know, like super low power hardware like this. This is like a kind of like a Raspberry Pi, but it's an NVIDIA something or other. So you can have a client that's optimized for low power hardware, or you can have a client that's optimized for like, you know, high-end server style hardware that has like 64 gigs of RAM, 128 gigs or whatever it is, right? So having a diverse set of clients is generally a good thing, I think, because you can make all kinds of optimizations and it's more resilient. So yeah, now that we have the clients, remember this is just code you run on your computer, people work on it, this code is stored somewhere, most of it's on GitHub, but you know, you could store it on any like source code, whatever they call it, like management service. And yeah, so a bunch of people contribute to these code bases, they fix bugs, blah, blah, blah. And by the way, when eth-research pushes out some new EIP, Ethereum Improvement Proposal, like some new thing that makes it through the gauntlet of eth-research, it eventually gets integrated into the spec, and the client teams work together to decide, okay, where's that change going to actually happen? Like we're going to take this change, usually they'll take a few different changes, like a few different things, and put them into one new release, right? And that'll be a fork, that'll be like Constantinople fork or Byzantium or whatever they're called. And so you'll bundle up a bunch of these changes into like an upcoming release, and the clients and everyone will agree on when that should hit. So they'll choose a block number. You don't choose like a time, because you know, like the block, you don't have, if you choose a time, then it becomes complicated getting the timing right for when the release actually hits. It's much simpler in the system like this to choose a block. So it's on this block, boom, in like approximately 6 months, we will have this new release go live. And then from there on, the system is using this new, you know, set of rules or whatever it is. And yeah, so you'll have some release, and it'll go live at whatever block. The clients will write all that code. They'll have it all ready prior to that actual fork happening. And they'll actually, what they'll do is they'll make the changes to their code, right? They'll push out a release. So they'll take that code, you know, they do all the checks and whatever, right? And then they'll push the release to the clients, to the actual nodes. These are the computers in the system that are running, you know, the Ethereum network. They're running this client code. So the clients will, ahead of the fork, right, they'll update their software, and then their node will be ready for the upcoming fork. And then when that block actually hits, the nodes don't have to do anything. It's not like they have to go fetch some new software at that moment, because that'd be way too, you know, down to the wire, right? They already have the code there, and it just turns on when block number equals the, you know, the agreed upon release block number. Then they just switch to the new rules, and the system updates. And yeah, so anyway, that's the way this Ethereum works. That's the way all or most of these systems work, is you have this process from research, a spec, you have clients, or at least one client. the changes happen on the client, the releases are pushed to the nodes. The nodes are all able to communicate and talk to each other, and that creates the system. In the case of Ethereum, this code, these Ethereum implementations running on all these different computers all over the world, this creates the actual Ethereum system, like as we understand it. And yeah, so this one other thing I'll mention is that each node is running like a complete copy of the Ethereum system. So every node in this network, they're all doing the exact same thing, kind of in step. Like every node in the system is the same in the sense that they're all running an implementation of Ethereum. Like which client they're running shouldn't matter. The clients, like, one thing I didn't mention about the clients is they're all implementing the spec, but the spec tells you, like, you know, the EVM has to function in this certain way and the blocks have to look like this and whatever. But exactly how you do that doesn't matter. Like, they're using different languages. They can have different architectures to how they lay out like the code. They can have all kinds of different implementation details as long as they follow the spec, you know, exactly, then it's all good. And so yeah, when you have this network of these nodes, they're all running one client or one of these clients. But as far as the network is concerned, it doesn't care. They're all just Ethereum nodes. They're just running Ethereum, and you know, every one of these nodes has its copy of the EVM. It has its EVM, and they all, you know, they receive a transaction. Like when you do a transaction, sooner or later your transaction will be broadcasted to a node. And you know, if this node like wins the block and mines your transaction, it's going to compute the state change to the system that results from executing your transaction. And it will, you know, propagate that block with your transaction in it to all these other nodes, and they're all going to do the exact same thing. They're going to process the block, they're going to process your transaction, and because they're all running a client which follows the spec, they'll all arrive at the same resulting state as a result of executing your transaction. So in this sense, the system is like, people have called it like a holographic system, in that the entire system, which is just our Ethereum with our state and everything, is like each piece of the system has the complete copy of the whole system in it, right? So like that's another thing that makes these systems so resilient, is because every node is running a complete copy of Ethereum. It has the whole history, in theory. It has the entire state, certainly. Like every contract on Ethereum, if you run an Ethereum node, you have every contract on Ethereum on that computer, right? Like it has a complete copy of the whole state. And because every node has that complete copy and it's working like independently, you can wipe out, you know, if there's a world war, you could wipe out 90% of the nodes. You could wipe out all of the nodes except like one or, you know, 2 or 5 or something, and the system would be fine. Like it doesn't break, it doesn't, you know, nothing happens because they're all a complete copy and they're just running independently. So anyway, yeah, this process is how you get this Ethereum world computer, which, you know, all of these nodes they're just simple computers. They're just regular computers, usually running Linux or Windows, but I think mostly Linux. And they're just running normal like Go code. It's nothing that fancy. The history and the state and everything of the Ethereum system on these nodes is just stored in their hard drive. Like there's no special like magical thing going on really. But the result of having this wide diversity of nodes all over the world is you get this, like you can think of it as this single kind of world computer, like a single computer, even though it's made of thousands or millions of underlying computers. It's this resulting holographic Ethereum world computer. So yeah, thanks for watching.